in this module we will discuss magnetic materials. We will first begin by looking at the traditional view of magnetism, that is classical electromagnetic view of magnetism, and then we will use those concepts to discuss various types of magnetic materials in a very brief manner, because to discuss magnetic materials it itself is a huge area and we would not like to do that one in this course, but we will give you the brief idea of what different magnetic materials are and what are their corresponding properties. So, to begin with, let us first look at what is the traditional view of magnetism. Before we can do that, let us actually recall what we have studied in the last few classes in terms of what magnetic fields are produced, right. So, we have actually discussed the use of Ampere's law or Biot-Savart's law in order to obtain magnetic field of current carrying conductors in various configurations. One of the simplest configuration that we considered was that of a long straight conductor which was carrying a current I, right, and then the magnetic fields around this long straight conductor was all in the direction of phi, and the magnetic field we know was given by I by 2 pi r. The magnetic field H was given by I by 2 pi r. We also considered a different geometry of that of a current that is carried around a loop, okay, of certain radius a, and here the magnetic field lines, especially the magnetic fields which are around at very far distance, right, they would all form these loops, okay, and we have shown that this fields which are at very far away distance was essentially equivalent to that of a, or in fact the nature of the fields was exactly equal to that of an electric dipole, right, an equivalent of an electric dipole. Of course, in the near region we were not in the calculation, we looked at this magnetic field in the far field region. There are a few additional geometries that are used to produce especially very high magnetic fields, okay. So, these are what are called as solenoids and toroids. They actually consist of a magnetic material which we are going to discuss sometime later, essentially a ferromagnetic material. They consist of current I, and then this current I is actually wound on a wire, and there is a magnetic material here, okay. So, this is the magnetic material around which the wires are which carry the current I are tightly wound and with a very narrow spacing between the wires, okay. And for the ideal case of an infinitely long solenoid, this is called as a solenoid. We have not discussed the field of a solenoid, which we will do very shortly. The fields of the solenoid are entirely inside that of the magnetic material, and they are all forming a line, okay, along the axis of the solenoid. Solenoid is essentially that cylinder. So, they all form lines, okay, and these are horizontal lines, and there are no fields outside this when the when the solenoid is infinitely large, okay. A different form of magnetic field generation that is used in some of the magnetic circuits is that of a toroid. A toroid essentially consists of a coil that has been wound, okay, in the form of a magnetic material that is bent, okay. So, it is a bent coil around which you are actually winding the current carrying wire. So, when you do that, the magnetic field turns out to be completely within this coil, okay. There are no magnetic fields outside the coil, okay. So, this toroid is especially useful for confining magnetic fields inside a given coil configuration, okay. So, to give you what is the magnetic field of a solenoid, consider this following Amperian law. So, assume that there is actually an infinite solenoid here, okay. So, there is an infinite solenoid which carries a current I, but since this is an infinite solenoid, we can actually characterize this by talking about what is the current per width or current per length, or equivalently the number of turns, right. Each turn carries a current I, so you can actually call upon this current per length. Instead of that, you can also talk about number of turns per length, okay. So, this multiplied by I would give you the amount of current per length. So, if you have say 10 turns per 1 meter and the current is around 1 ampere, okay, these are just random numbers which I am picking from my head, these are not the actual values. So, just to give you what the idea here is. So if the number of turns is 10 per meter, and then there are about then there is a current of 10 ampere in each turn, then the current per meter will be 10 into 10, 100 meters per, sorry, 100 amperes per meter. So you can actually think of this solenoid with its wires which are wound tightly around the solenoid on the outer surface of the solenoid as some sort of a sheet current flowing around the solenoid. Okay. So for such a solenoid, if you want to find out the fields, remember again the solenoid length is very large, which I am approximating as a infinitely long solenoid. For an infinitely long solenoid, if you are at any point, right, there would be an equal contribution of the current from one half, and there will be an equal contribution of the current from the other half, sorry, the magnetic field from the other half. And if you think of this solenoid as consisting of, you know, current carrying wires which are stacked one upon the other, you can see that the magnetic field on the axis coming from this would actually be along this way, right, and then there would also be another turn at the top which will produce a magnetic field along this. Okay. So if you look at, since the current directions would be opposite here, the total magnetic field would be along the axis of the solenoid. Okay. So this is how you can actually calculate the fields of a solenoid, which we are not going to do here. What we will do is we will assume an Amperian loop here, okay, of some length L, does not matter, we will assume an Amperian loop of length L and a certain width W. So in this loop what you have to observe is, if this is an infinitely long solenoid, then the magnetic field is of only this path, there will not be any magnetic field outside. So no H here tells us that there is no magnetic field outside that of the solenoid, and all the magnetic field is there inside the solenoid. Okay. This is an approximation which is very good when your length of the solenoid is very large, especially compared to its diameter or its this one. So with this as the Amperian loop, what would be my total current? So if the length of the path is L, then the total current will be Ni, correct, where N is the number of turns per meter multiplied by L will be the total number of turns, and then you can write this as NIL. Okay. Or if you were to consider N as the total number of turns inside this meter, then it would be N into I. Okay. So there are different ways of writing the same expression. What you have to understand is that each turn is contributing a current of I amperes, and therefore that if there are total of n turns inside the in the Amperian loop that you have considered, the total current will be n total into I. Okay. And what would be the left hand side of the Ampere's law? If you have forgotten Ampere's law, this is Ampere's law, right? Integral of H dot dl is equal to the total current enclosed. So we have actually obtained the right hand side, total current enclosed. For the left hand side, you can observe that there is no magnetic field along the path for W. So because the field is all perpendicular and along the axis, right. So there will only be one field which would be H, and the length of that one is H into L, right. So this would be equal to the total current enclosed, and therefore the magnetic field H, which would be along the axis of the solenoid, will be given by total turns in that loop L, I by L. Okay. Or you can talk in terms of the total current or turns per length, and then say N into I. If you want to obtain the B field, assuming that the magnetic material inside is filled with some mu 0 or mu r, then the magnetic field will be equal to mu 0 mu r N into I. So if you take this solenoid and instead of making it an infinitely long solenoid, you just take the solenoid and bend it around, forming a certain radius A, then you can see that the magnetic field would essentially more or less remain enclosed or more or less remain confined into the magnetic material itself. So there are no magnetic fields outside here. Okay. So with this brief introduction to solenoids, right, let us go ahead and look at the magnetic materials. We have already discussed dipoles. If you remember what a dipole was, the electric dipole was that of two charges which are separated by a certain distance, and the fields far away from the dipole were evaluated and it was given by certain expression. And interestingly, The same situation actually occurred for that of a wire that was carrying a current I. Again the far fields were all essentially given by the same expression, okay, the expressions were all the same as that of the dipole, okay. So which actually means that I can actually think of this current carrying loop as an equivalent dipole, except that now I have, you know, I am calling this as an equivalent dipole, except that I do not have electric charges, right. What I have is a fictitious magnetic charges, okay. So I have fictitious magnetic charges of plus qm and minus qm, okay, and these charges would produce a magnetic field which was exactly the same as that of current carrying loop. The far fields are essentially the same. So these are actually two ways in which people think of magnetic materials or magnetic dipoles especially, and magnetic materials are made up of magnetic dipoles. One is to think of them as tiny current loops, okay, carrying a certain current I and generating a magnetic field, okay. So if you take a material, you will find lot of such loops inside, okay, or you can think of them as equivalent magnetic charges. No doubt these magnetic charges are fictitious because they cannot be isolated and found in nature, but you can think of these magnetic charges, fictitious magnetic charges, as the same configuration as that of an electric dipole, which would produce exactly the same field, identically the same field as that of the current loop. In fact, the colloquial term for this magnetic charges used to be poles, and this is how the colloquial law of attraction was formulated earlier, like poles repel and unlike poles attract. So the pole would actually refer to the poles of a magnetic material, okay. So if you think of a matter, right, any magnetic material, just as we did for the dielectric materials, you can think of the magnetic material as consisting of tiny current loops, okay. Where are these current loops coming from? Well, matter is made up of atoms, right, and atoms have an inner nucleus which is positively charged and an outer electron which is negatively charged, but it would be moving around. The classical view of an atom is that of an atom moving around in a given orbit, right. So it would be moving around in an orbit generating a tiny loop of current, because if you imagine yourself at this particular point, you know, you are seeing yourself at this point, right, you will see that a charge is moving with a certain velocity or a charge is moving with a certain frequency and crossing this particular point corresponding to a current, okay. And there will be of course billions and billions of such atoms inside any macroscopically large magnetic material. You take a piece of magnetic material, there will be a large number of billions and billions of such atoms, okay, and each atom is essentially a tiny current loop. So the magnetic fields that are produced by each of these current loops will add up in the case of permanent magnets, okay. Permanent magnets are those which possess these tiny current loops, producing a magnetic field that would actually add up coherently. So if you take a magnet which is what, you know, a fridge magnet or a refrigerator magnet, then it will actually attract, and if you try to take some iron filings and then place this magnet slightly above it, then they would actually form a certain pattern. This is how we would actually visualize the magnetic lines of force or magnetic field, by taking a magnet, okay, a bar magnet or a round magnet, and then placing them with iron filings, and you will see that the iron filings would actually form a certain loop around this bar magnet, right. So this is because there is some magnetic field generated by these permanent magnets. There are no currents here, that is, there are no externally connected currents here. What we have instead are those tiny little loops inside this magnetic material, contributing to a overall magnetic field. Of course, to contribute to an overall magnetic field, you would of course expect that these tiny current loops must be aligned in some way, right. So this must be aligned in some way, okay. Only when they are aligned, then there will be a net magnetic material. If they are not aligned, they are completely randomly oriented, the magnetic moment of each of these current loop is completely oriented randomly, then there will not be any net magnetic field. Permanent magnets are those which actually have some magnetic field, and the reason is simply because they have this tiny current loops inside which are all aligned with each other. But please remember, if you take a piece of magnetic material, you will actually find a large number, billions and billions of such magnetic dipoles, right. So, each current carrying loop is actually a dipole. Okay. Of course, not many such permanent magnets are found, and even those permanent magnets that we find are dependent on temperature. That is, if you start increasing the temperature by heating up the magnet, after a certain critical temperature, okay, the magnetism actually breaks down. The magnetic material does not remain magnetic anymore. Okay. So, this is a problem that would happen even for a permanent magnet. So, in that sense, there is no permanent magnet independent of temperature, but for room temperature or for the temperature of operation that we are interested, the magnetic moments are permanent in the sense that they would be contributing to an external magnetic field. Okay. However, not many materials are lucky enough to have their moments aligned with each other. So, therefore, they do not actually possess magnetic fields. Okay. So, these two ways of thinking about magnetic materials is to think one of them as current loops having a certain magnetic moment M, or you think of them in terms of a fictitious bar magnet with plus magnetic charges, fictitious charges at one end, and negative magnetic charge minus QM, again fictitious at the other end. The far fields that are produced by these two configurations are exactly the same, and for our purposes one can model this magnetic field either by postulating a current loop, which is what one would find in a magnetic material made up of matter, okay, or you can equivalently think of them as charges. Now, one might ask, why should I think of them as charges? The reason is mathematical. Okay, of course, the reason is also historical, but if you forget history, the reason is mathematical, because when you think of magnetic charges, then whatever that we studied in terms of Laplace's equation or Poisson's equation, they can be applied directly to evaluate the magnetic fields of these configurations, right. Well, with one caveat, the fact that the magnetic field, the del cross H is not 0, means that this potential concept cannot be applied everywhere in the space. They should be applied in only those cases where the magnetic field is 0. Okay. So, with this idea as to why one should consider the two types of views of magnetism, we will then look at a little more detail into the modeling of magnetic material. Okay. So, to model magnetic material, we introduce, just as we did for the dielectric material. Remember what we did for dielectric material? We had these dielectric moments, and then we found, or then we said that we introduce a quantity called polarization P, which was supposed to be dipole moment, electric dipole moment per unit volume, right. So, we introduced this P, and then we introduced a new vector called D, and we related D to E and P in this expression. This is what we did for a dielectric material. Now, we are going to do this for magnetic material. So, which means that we are going to look at magnetic dipole moment per unit volume, call that as a certain vector M. Okay, just as we have polarization, we will have magnetization vector, and that magnetization vector will relate BH. Okay. So, let us do that. So, we define magnetization M as magnetic dipole moment per unit volume, and for the case of a permanent magnet such as a bar magnet, you can imagine this, remember this equivalent dipole thing that we were talking about. So, you can imagine them having a positive and a negative fictitious charge forming a dipole moment, right, and each of them can be thought of as north south pole. This is the traditional view of magnetization, having two poles north and south. North corresponds to fictitious positive charges and south corresponds to fictitious negative magnetic charges, right. So, for this one, if you assume that each of them has a length L or delta L, and then each of them has an area delta A, then the volume occupied by each dipole will be delta L into delta A, or one can actually talk of a group of dipoles. Okay. So, you are not really looking at an individual one, but you are looking at a group of dipoles which are average. So, this delta L and delta A are pertaining to those small regions, small enough to be considered as microscopic, but large enough to consider several magnetic dipoles together. Okay. So, with that the volume will be delta L delta A. This is tiny enough for us to define this magnetization M. Okay. So, we can say that delta V is equal to delta L into delta A, and the magnetic dipole moment, the equivalent magnetic dipole moment is Qm into delta L, right. So, this is exactly the same expression that you would have written for the electric matter. So, you have magnetic materials Qm delta L being the dipole moment. This of course is actually equal to current I into delta A, right. This is the current that is carried by the loop multiplied by delta A, that would be the magnitude of the dipole moment. So, when you actually look at this lot of tiny magnets inside a magnetic material, you will see that the north and south poles essentially cancel out each other, and what you are left with is some sort of a big dipole with all fictitious charges at the top and all negative charges at the bottom. Okay. So, this top charges are the north pole and the bottom charges at the bottom of this one is the south pole. So, what is the magnetic moment? Magnetic moment is Qm into delta L. Okay. So, what would be the magnetization vector M? The magnitude of the magnetization vector M will be Qm delta L into delta L delta A, giving me Qm by delta A, right. And if you consider the total such magnetic charges, this is was for a single dipole or a small enough region of a dipole. If you consider the total area, right, and total number of charges, total charges Qm, which is the sum of all these tiny dipole charges, and over the area A, which is the sum of this all delta A's, what you essentially get is a magnetic surface charge density, because this is charge per unit area. So, you get a magnetic surface charge density, and if you look at the top and the bottom surfaces of the bar magnet, you would see them populated with magnetic charges with a magnetic charge density plus rho Sm, and the south pole is all populated with negative magnetic charges or with a magnetic charge density of minus rho Sm. A similar equation can be obtained in terms of the current as well, because the magnetic moment is I into delta A. Just so that this is a magnetic moment, let us put a M subscript for the current carried by the magnetic dipole. Okay. So, this would be Im into delta A divided by delta L into delta A, right. So, if you look at this one, you will see that this is given by Im by delta L, and when you consider that entire length of the material, this would actually become Im by L. And what is this Im by L? What are the units of Im by L? The units of Im by L is current per meter, and this is precisely the sheet current that we talked about. Okay. So, the sheet current of measured in ampere per meter is another equivalent way of looking at the magnetic material. So, where does this come from? This actually comes from imagining tiny loops, right. All these loops in the interior of the magnetic material cancel with each other, leaving you the dipoles at the surface, which means an equivalent of a long solenoid with currents, right. So, with currents such that the current per, or if the number of turns is n, then the number of turns per meter into L into I will be the current enclosed per meters, right. So, it would be Nim by L will be the current that is enclosed up there. Okay. We will now look at the relationship between B, mu, H and M. We have previously introduced you to two fields, B and H. We did not really say anything about this relationship between the fields B and H. We just said that, well, in free space it so happens that B is equal to mu naught into H. Okay. So, H is measured in ampere per meter, if you remember, and B was measured in Webers per meter square, which was equivalent of Gauss, which also had an equivalent of Tesla, right. So, this was the traditional thing that we have introduced you to, but we did not really stress upon what was the relationship between B and H, except telling you that this is equal to mu 0 into H. What we can actually do is we can define experimental situation, or we can design an experiment which will actually bring out the relationship between B and H for free space and for magnetic matter. So, to do that, consider this solenoid, right, and then you wind up this solenoid with wire, okay, and the material that the solenoid is made up of is air. If you assume that the material made up of the toroid actually. So, if the material that is making up this toroid is actually air or free space, then the magnetic field we saw from the application of Ampere's law, or we could apply Ampere's law to give you that magnetic field as Ni by L, because there is only externally applied current I, and H0 is Ni by L, and because in the free space B is related to H by a factor of mu 0, B0 will be equal to mu 0 Ni by L. Now take the toroid, but except fill that toroid instead of with free space, fill it with a magnetic material, that is, take a magnetic material, bend it inside in the form of a rod, and then wind it up with current carrying wires, okay, of the same turns, and then apply the same current I. So, you apply the same current I. What will happen? The field produced must be of two different reasons, right. There is a field that is produced because of the external current, which is mu Ni by L, okay, no surprise out there, but these tiny loops inside the magnetic material itself, which will align, because this is a permanent magnet, it will align, and then it will contribute an extra field of its own, okay, and that extra field of its own will be some Nim by L. Note that I have not put any mu here, okay, we do not want to put a mu here, we just want to say that Im is the magnetic current, okay, or the current produced because of the tiny current loops inside the magnetic material, and if there are n turns and L is the length, then the total H field produced will be Nim by L, okay. So, this should actually be equal to the field B, correct. So, one second, let us actually write down this in a slightly different manner. So, initially let us put this mu 0 out here. So, we say B is equal to mu 0 into Ni by L, just to focus on the fields produced by the current. So, this is actually H field, right. So, instead of writing this B by mu 0, you could also have written as H field, and in the H field there is no mu 0, right. H is supposed to be independent of the magnetic material. So, H is given by Ni by L plus Nim by L, right. This H field will be equal to B by mu 0, okay. We assume that this H and B are still characterized by this mu 0. Of course, we will find that this is not exactly the same as H0 and B0, okay. So, H is B by mu 0, and this particular expression, which will give you B as mu 0 Ni by L, no surprise here, but you also get mu 0 Nim by L, okay. Now, we know that B and H must be related in a certain way, and this mu 0 Ni by L, we have already seen that it is equal to the H field. So, we get B is equal to mu naught H plus something else, and this something else is the magnetization M. So, what we have here is, and since there is a mu 0 sitting inside, so we need to multiply this one by mu 0 as well. So, what we actually have is a relation which says B is equal to mu 0 into H plus M. Equivalently, H can be written as B minus mu 0 M divided by mu 0, okay. So, if there was no magnetization, that is in the free space, whatever H is there, that would be equal to B by mu 0, okay. However, in the presence of magnetic materials, the magnetic field B would actually change from simple value of B to B minus mu 0 into M, and divided by that mu 0 will be equal to H, okay. In most cases, just like the case of a dielectric material, the relationship between M and H is that of linear, okay. Well, magnetic materials actually possess even more exotic properties, but we will not go into those properties at this moment, okay. So, M is linearly related to H, okay, and this relationship is defined by this parameter chi m. This is chi m is the magnetic susceptibility, just like you had sorry, P is equal to epsilon 0, there was an epsilon 0 at that because of whatever that reason is. So, epsilon 0 times chi E into electric field. Okay. We in fact evaluated the relationship between P and E and showed that it was linear for small electric fields, right. We looked at electric polarizability in terms of the atomic polarizability, ionic polarizability and oriental polarizability. Okay. So, similarly we will look at the relation between M and H for two classes of materials called diamagnets and paramagnets. We will keep the discussion brief, but give you the basic ideas of those materials. So, you have M is equal to chi m into H, again chi m is the magnetic susceptibility.